Welcome to the session on integration, the reverse chain rule. The objectives for this session are to integrate more complex functions by using the reverse of the chain rule. If you can write a function in the form k times f dash of x divided by f of x, then it can be integrated using the reverse of the chain rule for differentiation. Let's take a look at an example. Consider y equals ln mod f of x plus c, and let u equal f of x. So y equals ln mod u plus c. And this implies that dy du equals 1 over u. We also have that du dx equals f dash of x. And so, using the chain rule, we have that dy dx equals dy du times du dx, which is equal to 1 over f of x times f dash of x. And so if we integrate both sides with respect to x, we have y, which is of course equal to the integral with respect to y, equals the integral of f dash of x over f of x dx. However, we know that y equals ln mod f of x plus c. And so, if we plug this all in, we obtain that the integral of f dash of x over f of x dx equals ln mod f of x plus c. And so we can make a note of the general formula for the integral of k f dash of x over f of x and adjust for the constant k. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We are required to integrate x over x squared plus 4. So let's solve this. We're going to solve this by using the chain rule directly rather than the formula. We begin by letting I equal our desired integral. If we let y equal ln of x squared plus 4 and u equal x squared plus 4, then we have that y equals ln of u. We also have that dy du equals 1 over u and du dx equals 2x. If we apply the chain rule as shown, we have that dy dx equals 1 over u times 2x, which is equal to 2x over x squared plus 4. If we integrate both sides, we obtain y, because of course the integral with respect to dy is just y, and we also know that in our example y equals ln of x squared plus 4, but since we're integrating, we add the constant of integration. And of course on the right hand side we have integral 2x over x squared plus 4 dx. So we have this expression. We're actually required to integrate x over x squared plus 4, not 2x over x squared plus 4. So we need to adjust for the 2 and divide both sides by 2 to give us half ln of x squared plus 4 plus k equals integral of x over x squared plus 4 dx. Now let's take a look at part B. We're going to solve this by using our formula. First, we let f of x, which is the denominator, equal 3 plus sine x. And so f dash of x equals cos x. And of course, as you can see, this is our numerator in our example. And so if we apply our formula, we have that the integral of f dash of x over f of x dx equals the integral of cos x. Here, of course, we're plugging in f dash of x divided by 3 plus sine x dx. And this is, of course, equal to ln of 3 plus sine x plus c. And we have this from our formula. And so we have our integral. We're now going to solve part B using the other method. So let's let y equal ln of 3 plus sine x and u equal 3 plus sine x. This, of course, implies that y equals ln of u. And so dy du equals 1 over u, and du dx equals cos x. Plugging this into our chain rule gives us that dy dx equals 1 over u times cos x. And this is equal to cos x over 3 plus sine x. If we integrate both sides, and of course remembering that y equals ln of 3 plus sine x plus c, we have that y equals the integral of cos x over 3 plus sine x dx. Suppose that we can write a function in the form k times f dash of x times f of x to the power n. Then it can be integrated using the reverse of the chain rule for differentiation. Let's take a look at an example. Consider y equals f of x to the power n plus 1 plus c, and let u equal f of x. So we have that y equals u to the power n plus 1 plus c. And this implies that dy du equals n plus 1 times u to the power n. We also have that du dx equals f dash of x. So using the chain rule, dy dx equals dy du times du dx, we have that dy dx equals n plus 1 times f of x to the power n times f dash of x. And so if we integrate both sides with respect to x, we have y equals integral dy equals integral n plus 1 times f of x to the power n times f dash of x dx. However, we know that y equals f of x to the power n plus 1 plus c, and therefore we can equate this to the integral we have. We have an n plus 1 inside the integral sign, which we can also take outside, and dividing both sides by n plus 1 gives us this expression. So let's save this general formula on the left-hand side of the screen, as shown here. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. Let's take a look at part A first. We're required to integrate the function sin x to the power 5 times cos x. So let's solve this using the first method. We begin by putting I equal to our integral and then compare it to the formula that we have. Notice that we have sin x to the power 5, but we also have in our formula f of x to the power n. Notice also that if we differentiate f of x, we should get f dash of x. And so, looking in our integral, we have that if we differentiate sin x, we obtain cos x. So we can actually apply this formula. So we let f of x equal sin x, and of course this implies that f dash of x equals cos x. So our integral I is equal to sin x to the power 5 plus 1, because of course n equals 5, divided by 5 plus 1, which is of course n plus 1 also, plus our constant of integration. And tidying this up gives us that our integral is sin x to the power 6 divided by 6, plus the constant of integration. Now let's solve this using the other method. Again, we let I equal our integral. This time we put y equal sin x to the power 6 divided by 6 and u equal to sin x. So we have that y equals u to the power 6 divided by 6. And so dy du equals u to the power 5 and du dx equals cos x. Using the chain rule, as shown, gives us that dy dx equals u to the power 5 times cos x. And this is equal to sin x to the power 5 times cos x. And integrating both sides, we have y, which is of course the integral dy, equals integral sin x to the power 5 cos x dx. And so we have our integral as shown here. Now let's take a look at part B. Given that the integral of sin x to the power 5 times cos x dx between the limits pi and theta equals 0, where theta is greater than pi and less than or equal to 2 pi, find the exact value of theta. So let's solve this. Now from part A, we have that the integral of sin x to the power 5 cos x dx equals sin x to the power 6 over 6 plus c. So the integral that we have, namely integral between the limits pi to theta, is equal to sin theta to the power 6 over 6 minus sin pi over 6. And from our assumptions in the question, this is equal to 0. And therefore, we're going to solve for sin theta to the power 6 over 6 minus sin pi over 6 equals 0. Notice that sine pi is actually equal to 0. So we can replace that as shown, to give us that sine theta to the power 6 is equal to 0. Now sine x equals 0 at 2 pi, in the interval theta greater than pi and less than or equal to 2 pi. Therefore, theta equals 2 pi in this interval. This brings us to the end of this session. If you have understood its contents, you should be able to integrate more complex functions by using the reverse of the chain rule. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.